Today we're going to talk about solving inequalities. And inequalities are a little bit different than equations. They're mostly the same, except for instead of using an equal sign, we're going to be using these symbols here: greater than, less than, greater than or equal to, or less than or equal to. So just to recap what we learned in the past, a linear equation in one variable can be written as ax plus b equals 0, where a does not equal 0. And the solution to a linear equation in any value of a variable that makes the equation true. There is only one solution to a linear equation. I'm actually going to put an asterisk here. That is not necessarily true. Okay? Have you guys seen the meme? I don't know. I like all these different Facebook pages, or math pages, right? Math teacher pages. So there's this meme that keeps coming up, and it says, math. I wish I had it right here. Math. It gives us hope that all problems have solutions. And I say to that, no, math doesn't actually do that. Sorry. Rain on your parade. There are some equations that have no solution. For example, if I said 5x plus 5 is equal to 5x, this says 5 times a number plus 5 more is equal to 5 times that same number. Is that true? Let's see what would happen if I try to solve that. What would I do if I tried to solve that? I would subtract 5x from both sides, right? And I would get what? 5 equals 0. Is it true if I have $5, do I also have $0? No, 5 does not equal 0. So that would be an example of an equation that had no solution, right? It's what we call a contradiction. It could never be true. You could also have equations that have all real numbers. If I say 5x is equal to 5x, maybe I even say 5x plus 2 is equal to 5x plus 2. This is saying 5 times a number plus 2 more is equal to 5 times a number plus 2 more. If I try to solve this one, I subtract 5 from both sides. I get 2 equals 2. Is 2 equal to 2? Yeah, so this one is always true for all real numbers. Okay, this one is never true, so we say there's no solution. Okay, these are two special cases. I only wanted to bring this up because I was having a conversation with a math teacher that also teaches Math 60, and we were saying, there's only one solution to a linear equation. It's not necessarily always true. I'm not asking you to memorize that right now. I'm just trying to point out that sometimes we can have contradictions and sometimes we can have statements that are universally true. Okay? So we're just doing a little addendum there. Okay, now let's talk about inequality. So an inequality is a number sentence in which we use these symbols: greater than, less than, greater than or equal to, or less than or equal to. And that's the verb we're using instead of equals, right? Is or equal to. A solution to a linear inequality is any value of the variable that makes the inequality a true statement. A linear inequality will have infinitely many solutions. And I should put an asterisk here too, because it could also fall into that same category. You know, what if I said something like 5x is, I don't know, greater than 5x minus 2, right? So think about that for a minute. Oh wait, no, actually, let's say plus 2, sorry. I'm fixing it up. If I were to solve this, 5x, I would get 0 is greater than 2. Is 0 greater than 2? No. So again, we could have infinitely many solutions, or we could also have a statement that's like never true. So we could have no solutions. But mostly we're going to be dealing right now with inequalities that have infinitely many solutions. Okay. The set of solutions is called the solution set, and we can use a graph to help us represent the solutions to an inequality. So if we start by graphing the solution sets, we might draw a number line, and on this number line, it's kind of good to put 0 here. Here's 9 up in the positive direction, and down here would be negative 9. So maybe we have 3 numbers, and we're just representing where those numbers are on the number line. Now, how would you read this statement? X is less than 9. So that's a lot of different numbers. Can you give me some examples of numbers that are less than 9? 8. Good. What else? 5, 4, 3, 2, 1, 0. Oh, can you list them all? No, because how many numbers are less than 9? There's an infinite number of numbers that are less than 9. So what we would do is we would say, I'm not going to include 9. I'm going to put a parenthesis on 9, otherwise known as an open circle, because I'm not including 9. Is 9 less than 9? No. And then I'm going to shade all the way down, and this shaded area is all of the numbers that are less than 9. Of course, I cannot list all of them, so I'm shading the arrow in to show that it's going to keep going in that direction. Yes, question? Exactly. So you can do a parenthesis, or you could do an open circle here. I'll do them both to show. Yes, if it's included, you would do a closed circle. So let's try this one now. And this one says, what is this? How do you read that one? Yes, X is less than or equal to 9. And this one, we could put a bracket, and the bracket means 9 is included, whereas the parenthesis means 9 is not included. Okay, and again, less than or equal to, so we're shading this whole direction, and we're shading the arrow in, showing that it's going on towards negative infinity. The other variation that you might have seen before is here. This one reads, how would we read this one? Yes, X is greater than or equal to negative 8, so I'm going to draw my number line. I'm going to start here with negative 8. Over here is 0. Over here is 8, just so we have some landmarks. Greater than or equal to, if I circle it and shade it in, that means 8, negative 8, is included. And then where are we shading? Below negative 8 or above negative 8? Above, because what are some numbers that are greater than negative 8? All of the numbers that are above negative 8. Good. Okay, and some examples could be 0, that's included. 8 is also included. Okay, now this one is kind of written a little bit backwards. How would you read that one? 5 is less than X. This could be the same thing as X is greater than 5. Now I want to show you something. You can write it this way. 5 is greater than X, or sorry, less than X. X is greater than 5. Do you see how those are kind of like mirror images of each other? If you write the variable on the left-hand side, and here's 0, here's 5, here's negative 5, your arrow is going to point in the same direction. So here we would do an open circle, meaning that 5 is not included. And notice that if the X is on the left, your arrow points in the same way, your inequality, I should say, points in the same direction that you're shading. Okay? But if it's written on the other side, you would kind of have to do a mirror image flop. Haley? Okay, so the dot right here, I'm just showing you two different ways you can do it. The bracket and the dot, filled in dot, mean the exact same thing. And circle and parentheses mean the exact same thing. And it's going to be helpful later because when you get to chapter 2, we're going to start talking about different kinds of notation. How many people have heard of set builder notation? Don't worry about it. You're going to learn about it, okay? What about interval notation? Have you heard of it? That's okay. You're going to learn all about it. Here's a sneak preview. The interval notation for this is just FYI, you will learn it later, is going to be from negative infinity to 9 parentheses. That's why I bring up the parenthesis now, is because you're going to use that parenthesis to show that the 9 is not included. The interval notation for this one would be from negative infinity to 9 bracket. And the only difference here is that the 9 is included because of the or equal to, and the 9 here is not included because there's no or equal to. Okay? If you were going to do interval notation for this one, you would have negative 8 to infinity. You see the difference? Oops, except for we're including the 8, so sorry. Bracket. And then this one would be from 5 to infinity. You see the parenthesis means the number's not included. So it's kind of nice if you use the bracket and the parenthesis on the graph, because then it helps you write the interval notation. Okay, you don't need to know the interval notation just yet, but it's always good to like hear about it and then hear about it later. Yes. Well, no, that's why we put the parenthesis. It wouldn't be 6 to infinity, because think about how many different numbers are there. All the way up here is 6. How many numbers are there between 5 and 6? Yeah, what are some examples of numbers that exist between 5 and 6? 5.1. What about 5.000000001? You see, what happens is actually on a number line, even between the numbers, on the number line between 0 and 1, how many numbers exist between 0 and 1? Yeah, because you can continue to break it down into an infinite number of fractions. So that's so crazy to think that there's an infinite number of numbers, even just between 0 and 1. Those are all what we call proper fractions. All of the proper fractions that you know of that exist, which is an infinite number, is between 0 and 1. Isn't that amazing? That's kind of mind-blowing. Kind of reminds me of Zeno's paradox, you know? What is Zeno's paradox? Does anyone know that? It's like, if I start at one wall and I walk halfway across the room, and then I walk half of that distance, and then I walk half of that distance, can I ever get to the other side of the wall? The other end of the room? No, because I can keep, it's other words, it's also kind of like the Cookie Monster problem. The Cookie Monster eats half of a cookie one day, and then the Cookie Monster must be on a diet, because the next day he eats half of that half. And then the next day he eats half of that half. You see what's happening here? Here's your cookie, half of the cookie, half of that half, half of that half, half of that half. Okay, will the cookie ever get eaten? No. And this is kind of like if you take a chemistry class, you might think about exponential decay. We could get into all kinds of advanced math over this question, though. But that's a really good question that a lot of people will like. If 5 is not included, why not start at 6? But does that kind of make sense now? Does that answer your question as to why we would say we can't include 5? But there's no way to get right next to 5. Do you know what I mean? Well, no, because we're not including 5. So we're open circle. 5 is not included. Right. Okay, let's go on to the next one. Write an inequality for each graph. So if we look at this, where are we starting and where are we ending? We're starting at 3. So how could you describe this situation? Down here is positive infinity. Okay? So who can tell me the inequality that would describe this graph? Let's start with x is. X is what compared to 3? It's greater than 3. Is it including 3? So it's greater than or equal to. Okay, what about this one? Down here, by the way, is negative infinity. The arrow says, I don't stop. I keep on going. X is less than negative 7. Notice how your arrow and your inequality point in the same direction if you start with X on the left. So it's easier to, if you can always force X to be on the left, then you'll know your graph is going in the right direction if you check where the arrow is going. Yeah?